Weight Shift Control 6-4 Flight Maneuvers. When it comes to managing energy in a weight shift control aircraft, you've got to keep in mind that these things don't have much momentum due to their lightweight. It's all about handling kinetic energy, and that means higher speed and power translate to higher energy. Lower speed and power, on the other hand, mean lower energy. Pilots need to master the art of maintaining high energy levels, especially in turbulent air and close to the ground. This is the foundation of energy management for weight shift control. Starting off, energy management practices should kick off at higher altitudes. Picture this. While cruising straight and level, you're playing with the power, increasing and decreasing it, all the while adjusting the pitch. Begin at the trim position with the appropriate cruise throttle setting. As you smoothly apply power towards full throttle, the pitch attitude of the weight shift control aircraft wants to climb. To counteract this and maintain level flight, you'll need to decrease the pitch, keeping that energy level high. Now, after holding this application for a few seconds, it's time to smoothly reduce power to the cruise setting. As you do that, increase the pitch to maintain your level flight. This brings the weight shift control back to a lower trim or cruise power, settling into a medium energy level. Next up, you repeat the cycle. Increase power, decrease pitch to stay level, reaching a high energy level. Then, reduce power to idle, let the nose drop, and increase pitch. This is a critical phase because the energy levels are decreasing, often a sign of trouble when approaching the runway. The pilot should be quick to recognize this and apply power promptly to prevent a descent. It's not just about energy management. You also need to be mindful of slow flight and stall characteristics, ensuring you maintain a specified heading. Once a pilot masters this maneuver at higher altitudes, it's time to practice energy management with low passes down the runway. Start with higher energy levels, then transition to lower trim or cruise power at medium energy, and finally, the higher to medium trim or cruise power energy levels. Those low passes fine-tune a student's skills for energy management and serve as an excellent preparation for landings. Understanding that higher energy levels are crucial when maneuvering near the ground, especially in turbulent or crosswind conditions, is vital. It's also suggested for a power-on approach with higher airspeed than the normal approach speed and increased power, giving the weight shift control aircraft more overall energy to handle turbulence and crosswinds. Now, moving on to slow flight and stalls, maintaining lift and control in slow flight requires hitting a minimum airspeed and angle of attack. Stalling speed is that critical point where controlled flight becomes impossible, and pilots must develop a sense for that margin above stalling speed. Knowing how the aircraft responds at different airspeeds is crucial for safe operation in slow flight conditions. In slow flight, there are two distinct speeds to consider: VX and short field descent speed discussed earlier, and minimum controlled airspeed. The latter is the slowest airspeed at which the aircraft can maintain controlled flight without risking a stall, usually 2 to 3 knots above stalling speed. Maneuvering at this speed involves reduced power settings, with the airspeed sufficiently above the stall to allow maneuvering but close enough to sense the characteristics of flight at very low airspeed. Frequent reference to flight instruments, especially the airspeed indicator, is essential during slow flight to develop a feel for the aircraft at these low speeds and to operate with precision. The goal of the minimum controlled airspeed maneuver is to fly straight and level and make shallow level turns at that slow speed. Start by flying the weight shift control at trim speed straight and level to maintain a constant altitude. Then, raise the nose as you reduce the throttle to maintain that constant altitude. As the speed decreases further, you'll notice changes in the feel of the flight controls, pitch pressure, and the increased difficulty of maintaining a straight heading. Eventually, you'll need to increase the throttle to stay level after the weight shift control has slowed below its maximum LD speed. Pay attention to the sound of the airflow as it changes, and keep in mind the manufacturer's specifications. Usually, the control bar should not be touching the forward tube at minimum controlled airspeed. In a nutshell, energy management, slow flight, and stalls are integral aspects of flying a weight shift control aircraft, demanding a pilot's keen understanding and mastery for safe and precise operation. When flying below the minimum drag speed, LDMAX, it's crucial for the pilot to be aware of a characteristic known as speed instability. At speeds less than LDMAX, the aircraft becomes prone to speed instability. Even the slightest turbulence can disturb the aircraft, leading to a decrease in airspeed. As the airspeed drops, the total drag increases, causing a further loss in airspeed. Unless corrective action is taken, such as applying more power or lowering the nose, the speed will continue to decay, potentially leading to a stall. This speed instability is a critical factor in slow flight, and pilots must understand that allowing the airspeed to decay below minimum drag speed can result in unstable conditions. It's worth noting that the amount of power required to maintain level flight at minimum controlled airspeed is greater than that needed at the minimum drag speed, which also happens to be the best glide ratio speed and the best rate of climb speed. Once the aircraft's attitude, airspeed, and power have been stabilized in straight and level flight, it's essential to practice turns to understand the controllability characteristics at this minimum speed. During turns, adjustments in power and pitch attitude may be necessary to maintain the desired airspeed and altitude. The objective is to familiarize the pilot with the limitations of maneuverability at minimum controlled airspeed, the potential danger of incipient stalls, and the aircraft's tendency to stall as the bank is increased. Stalls at this critical airspeed can occur due to turbulence or abrupt control movements. Establishing a descent or climb at minimum controllable airspeed is possible by adjusting the power to achieve the desired rate of descent or climb once flight at this speed is properly set up for level flight. Errors in slow flight involve inadequate area clearance, improper forward pressure adjustments causing altitude fluctuations, and issues like excessive pressure leading to climb or mushing, alongside problems managing power and attention between control and orientation. Moving on to stalls. A stall occurs when the smooth airflow over the aircraft's wing route is disrupted, and lift degenerates rapidly. This happens when the wing route exceeds its critical angle of attack, and it can occur at any airspeed, in any attitude, with any power setting. Training in stall recovery and developing an awareness of stalls are critical aspects of pilot training. The objectives of intentional stalls are to familiarize the pilot with conditions that lead to stalls, recognize the signs of an approaching stall, and instill the habit of taking prompt preventive or corrective action. Pilots need to identify flight conditions conducive to stalls and apply the necessary corrective action. Pilots detect an impending stall by positioning the control bar forward, observing the aircraft's attitude relative to power settings, sensing the wind's change on the structure and themselves, and noting kinesthetic shifts. This awareness, particularly crucial for trained pilots, signals speed reduction or the onset of aircraft settling or mushing.